Welcome to this MOOCs online video course Theory of Yarn Structure. In the last two classes we discussed about module 8 Tensile Mechanics of Yarns. We started with discussion on mechanics of parallel fiber bundle. There we discussed Hamburger's theory and also we solved two numerical problems. Today we are going to start with the third numerical problem on module 8. So, this problem is basically an extension of problem number 1 of this module. You remember in problem number 1 this information was given: cotton fibers possess a tenacity of 0.36 Newton per tex, breaking strain 11%. Polyester fiber possesses a tenacity of 0.41 Newton per tex and breaking strain 46%. Further, the polyester fiber shows specific stress of 0.12 Newton per tex at a strain of 11%. Determine the blend ratio of cotton and polyester fibers at which the bundle's tenacity will be the minimum. Also determine the strength of the corresponding bundle. So, what information are given? Let us summarize. P1 by T1 is equal to 0.36 Newton per tex is given. We consider 1 denotes cotton and 2 denotes polyester. Okay. Then another information is given: P2 by T2 0.41 Newton per tex. Breaking elongation is also given here. Breaking elongation is also given here. Another information which is given as S2 A1 divided by T2 is given as 0.12 Newton per tex. So, these all information are given. We have to determine the blend ratio at which the bundle tenacity will be minimum. This we have already derived in the last class. We will straight away use the expression here. So, the bundle tenacity will be minimum when G2 is equal to P1 by T1 divided by P1 by T1 plus P2 by T2 minus S2 A1 by T2. So, these data are given here. What is P1 by T1 is given as 0.36 plus P2 by T2 is given as 0.41 minus S2 A1 by T2 is given as 0.12. So, this value will come as ratio of 0.36 to 0.65, which is equal to 0.55. That means, when so G1 is 1 minus G2 0.45. When cotton fiber mass percentage is 45 and polyester mass percentage is 55, the resulting bundle gives the minimum strength. So, this was the first part of the problem. Now, the second part is what will be tenacity of this bundle, consist of 45% cotton fibers and 55% polyester fibers. So, let us solve that part of the problem. As we know, bundle tenacity is the minimum of two values, right. So, here G1 is given as 0.45 and G2 is given 0.55. So, minimum of two values 0.45 into 0.36 plus 0.55 into 0.12 comma this value 0.55 into 0.41. So, these is a maximum. Maximum of these two values. So, these two values will come 0.228 and 0.226, which will be equal to 0.228 Newton per tex. So, the bundle consisting of 0.45%, 45% cotton fibers and 55% polyester fibers will show minimum strength. And what is the minimum strength? Minimum strength is 0.228 Newton per tex. So, this is the answer of the second part of the problem. Now, we will discuss another numerical problem, the fourth one, which is basically an extension of problem number 2. If you remember, in problem number 2 in this module, we calculated bundle tenacities when cotton and polypropylene fibers of given data were blended at different proportions. In this particular problem, what is asked is the minimum determine the strength of the weakest bundle. So, in problem number 2 also these information were given. P1 by T1 is equal to 0.36 Newton per tex, then A1 0.11, same data were given in problem number 2. P2 by T2 0.53 Newton per tex, A2 0.25, another information is given, S2 A1 by T2 0.30 Newton per tex. Now, we have to first find out what is the blend ratio at which bundle tenacity will be minimum. Then we have to determine the strength of the bundle at that particular blend ratio. So, let us first determine what is the blend ratio at which bundle tenacity will be minimum. So, in this particular problem, 1 subscript 1 denotes cotton and subscript 2 denotes polypropylene. So, the blend ratio at which bundle tenacity will be minimum is equal to P1 by T1 plus P2 by T2 minus STA1 by T1 is this. Now, in this particular problem, P1 by T1 is given as 0.36. P2 by T2 is given as 0.53 minus S2A1 by T2 is given as 0.30, right. So, what will be this value? 0.36 divided by 0.59. So, this will be equal to 0.61. Then what is G1? G1 is 1 minus G2. So, 1 minus 0.61, so 0.39. What does that mean? The blend ratio cotton 39%, polypropylene 61%. So, a bundle which consists of 39% cotton fibers and 61% polyester fibers gives the minimum tenacity. Then what is the minimum tenacity? So, now we will solve that part of the problem. So, minimum tenacity will be obtained in this manner. Right. So, here what is your G1? 0.39. What is P1 by T1? 0.36 plus what is Z2? 0.61. What is S2A1 by T2? 0.30. So, this is one value. The next value is 0.53. So, there will be two values 0.3234 and another will be Newton per text is the answer. So, the bundle which gives you minimum tenacity, where the minimum tenacity is 0.3234 Newton per text, and that bundle consists of 39% cotton fibers and 61% polypropylene fibers. So, far we have solved 4 numerical problems. Now, we will go to discuss the next part of this module, that is related to stress strain relation in yarn. So, we will now start that part, stress strain relation in yarn. If you remember, on the first class of this module, we told that in this module we will be going to discuss two things. One is the tensile mechanics of parallel fiber bundle, second is the stress strain relation in yarn. So far we have discussed the tensile mechanics of parallel fiber bundles, now we are going to discuss about stress strain relation in yarn. So, this part we will start with a diagram. This diagram is very much related to the diagram that we discussed in the module of radial migration of fibers in yarn. What we see here is there is a general fiber element, dl is its length, this element. So, as we know from the module of radial fiber migration in yarn, where we talked about general fiber path, fiber element, different angles. So, this fiber element, initial fiber element of length dl is characterized by three quantities. One is d zeta, second is r, second is r, and the third is the angle beta. Now, we are applying load force to the yarn, as a result yarn elongates. So, dl prime is this length, this part you are not seeing. dl prime is the length of the fiber element after elongation of the yarn. So, the axial position is changing. So, this is the increment along the axis of the yarn, its radial position is changing and also its angle is changing. So, these three quantities determine the position of the fiber element after elongation of the yarn. Now, if we see this top picture, this is the length dl, length of the fiber element, angle of the fiber element to the axis of yarn is beta, this width becomes r times d phi and this is d zeta. After elongation, this fiber element will change its position, this change is shown here, the length becomes dl prime, angle becomes beta prime, as a result the width becomes r prime d phi and the length axial distance becomes d zeta prime. So, this is about this image. Now, we will define three quantities. One is yarn axial strain. Yarn axial strain, we use this symbol epsilon subscript a. This is the change in the axial distance divided by the original distance. So, what is the change in the axial distance? D zeta prime minus d zeta is the change in the axial distance divided by original distance is d zeta. So, d zeta prime minus d zeta by d zeta. So, this is equal to minus 1. So, we obtain 1 plus epsilon a d zeta, right. Second is the radial strain. How do we define radial strain? Radial strain is the change in radius divided by original radius. We denote this by epsilon r. What is the change in radius? R prime minus r is the change in radius divided by original radius. So, this becomes r prime by r minus 1. So, r prime is equal to r into 1 plus epsilon r. Then we define contraction ratio similar to Poisson's ratio. What is Poisson's ratio? Is the ratio of radial strain by axial strain. So, we define contraction ratio is like Poisson's ratio. We use the symbol eta for that, is equal to minus radial strain by axial strain. This gives you minus eta times this. The last quantity is fiber strain. Because of the application of force, the fiber is also stressed, it also exhibits strain. So, what is fiber strain? Fiber strain, let us use this symbol epsilon L. Again, it is defined by the ratio of change in fiber length divided by original fiber length. What is change in fiber length? dl prime minus dl is the change in fiber length divided by original length. So, dl prime divided by dl minus 1. So, dl prime is 1 plus epsilon L into dl. So, if we summarize these 4 quantities, first one was d zeta prime is equal to this, second one was new radius 1 plus epsilon r, third was contraction ratio, and the fourth is this one. Right. Our next step, if we come back to the original drawing, our next step will be applying Pythagorean theorem to this triangle and also to this triangle. So, if we apply Pythagorean theorem, let us see what happens. dl square is equal to r d phi square plus d zeta square. So, let us write down dl square is equal to r d phi square plus d zeta square. dl square is equal to r d phi square plus d zeta square. Similarly, if we apply Pythagorean theorem to this triangle, then we will see dl prime square is equal to r prime d phi square plus d zeta prime square. So, let us write down square r prime d phi square plus this. You see one more time, this square is equal to this square plus this square. Okay. Now, we use our 4 basic relations. R prime was equal to r times 1 plus epsilon a r d phi square. This was equal to r prime, right. And what is your d zeta prime? D zeta prime we have derived square. So, if we rearrange it, then it becomes 1 plus epsilon a square plus 1 plus epsilon r square d phi square, right. Further, epsilon r, this epsilon r is equal to minus eta into epsilon a, definition of contraction ratio. So, what we obtain is squared plus 1 minus squared r d phi square, right. We continue with derivation. What is your dl prime by dl square? dl prime by dl square was defined by one plus this. So, 1 plus epsilon L square is this divided by this. We have just now derived dl prime square is this. So, we write this in the numerator, 1 plus epsilon A squared square plus 1 minus eta epsilon A square r d phi. In the denominator it is dl square. So, by using Pythagorean theorem we obtain this relation, we will use this in the denominator. So, we write this as squared plus r time d phi square. Now, we divide numerator as well as denominator by this quantity d zeta square. Let us see what we obtain. One plus epsilon square 1 minus eta square r d phi by d zeta square 1 plus r d phi by d zeta square. What is this quantity r d phi by d zeta? We come back to our diagram. Tangent beta, tangent of this is equal to r times d phi by d zeta. So, r times d phi divided by d zeta is equal to tangent of beta. So, this quantity is equal to tan square beta, right. So, we substitute this, then what we obtain is squared plus 1 minus we stop here today. In the next class we will continue from this expression. Thank you very much for your attention.